Well, recognizing that I'm all that's standing between you all and happy hour, I will try to make this concise and relatively engaging. So I do want to thank Danielle and our host here at the Wood Education Research Center for hosting this conference. I think what I'm supposed to do is talk a little bit more about some of the technology options, specifically around biofuels. And I think you've gotten a real good feel for some of the production issues. You know, what can we grow, where do we grow it, and what are some of the carbon cycles around what we do. And as I think Jim did a good job of highlighting, that if we're making paper, if we're making wood, if we're even making pellets, arguably you can go measure the productivity of that unit operations. We've got them. Right? You can go measure the number of logs that go into a plant, the number of 2x4s that come out, the number of chip trucks that go into a mill, and the number of rolls of paper that come out, heat and power, and all those flows. The real challenge with bioenergy products, as Jim kind of alluded to, is starting to model that thing that we have not yet built. And there are a lot of details that I'll touch on, a few of them, around connecting the biomass to the production process to the final product. That not every ton of biomass is equal for every production process or every product. So that said, the feedstocks are not all useful, as I just said. The other thing we need to be careful of is trying to talk about an opportunity. I am going to make money on this play, and I frankly don't care about carbon flows or the worldwide, national, statewide availability of biomass. I want to make money right here. So there are lots of opportunities, and many times we confuse those with, here's the opportunity, this is a good business play, and we're not going to do 50 of those. So the fact that it maybe strains a resource or it strains a particular attribute, you've got to separate those two items out. We are rarely clear about the value chain. We all kind of know this, but I think we've got to really be explicit. Chemicals are worth more than fuels, is worth more than electrons, is worth more than heat and power. So you can talk about using 93% of the caloric value in a process. That doesn't say you're going to make money on it. Okay? So again, specific details are real important. When we talk about manufacturing, we need to talk about cost, or beg your pardon, yeah, about cost, not just the price. Okay? So the fact that something's worth a lot, the classic example that frankly many of the folks at the university in our department talk about is, I'm going to make pyrolysis oils because there is a vinyl phenol in there, and vinyl phenol is worth $10 a pound. So what? You can't get the vinyl phenol out of that mixture of pyrolysis oil come hell or high water. Okay, so the fact that you've got something in there that may have value doesn't mean you can make a commercially viable deal out of it. And manufacturing 101. Now there are, again, to my opportunity point, you can always find, not always, you can frequently find a niche opportunity. Biodiesel, fatty acid methyl esters, to me is a really good example, where there are people doing a great job making money on small scale production. But those are arguably, I would maintain, a lively discussion that I've had with some of my colleagues in North Carolina about this. Those are one-off deals. There aren't a lot of small paper mills. There aren't a lot of small chemical plants. There aren't a lot of small petroleum refineries. And there's a reason for that. Bigger is cheaper per unit of product. Okay? Even with biomass, even with this collection radius, okay? Bigger is cheaper. Now, at some point, you're going to run into other drivers other than simple production cost. But bigger is cheaper per unit of product. Another point that I know DOE is making that frankly I don't think we collectively make or realize explicitly is essentially the demand for ethanol is finite, and frankly it's pretty well saturated with corn ethanol. All right, the so-called blend wall. So right now in the U.S., we can put about 10% of the ethanol in gasoline. EPA's raised it to 15%. None of the auto companies like it. That's a little bit of a conundrum right now. But in the U.S., all we're doing, let's say, for the sake of argument, is we're going to put 15% of ethanol into the gasoline pool. We're almost there. Okay? So what's the demand for biofuels? What's the driver? Well, you've got to start making diesel, you've got to start making other hydrocarbons, you've got to start making jet fuel. None of those are going to come from ethanol. So as you start to think about what technologies are going to get you down the road, you need something that starts to make hydrocarbons, or we have to completely change our distribution and transportation system to do engines like they do with the parts. It's not the engines per se. But the automotive system, like they do in Brazil, where you can, on any given day, you can put whatever you want in your car. Go back and forth, okay? But right now, we're not there. This is my attempt to show a whole variety of feedstocks, a whole variety of conversion processes, and a whole variety of products. And again, I think one of the challenges, we tend to say we can do anything with biofuels. Anybody that's got 40 acres has got a biofuels play. They're in the game. They're ready to go. You know, and the details get real important. What are they growing? How are they growing it? What are they going to make? What scale are they going to make? Okay. And as we talk about technology and commercial opportunities, those details are important. And I would argue, again, we collectively don't do a good enough job at drilling into those details as quickly as we should. So I think some of you have seen my chart here before. This is a little bit dated now. The real point, do I have a, pardon me. The real point of this is kind of twofold. The first one is that if you look at 100 units of energy in, this is basically all the energy inputs in the United States. These are the products, the industries that use it, product out. And about 55% of our energy going in is wasted. So if you talk about actually having an impact on energy, the first thing is energy conservation. As trite as it may seem, turn off the lights. All right? Turn your thermostat down a degree or two. I mean, those things matter if we would all get on board. But the second point I want to make is, frankly, biomass right here is about 3.5% of our current energy grid. And this little skinny line here from biomass is the equivalent of 9 billion. This information is a little bit old, so when that was made, it was about 9 billion gallons of ethanol. Okay, let me say it again. That little line, think of those as pipes. So that little pipe carries 9 billion gallons of ethanol, corn ethanol. Okay. That's more than the undergrads drink on a football weekend. I mean, that's a lot of alcohol. Okay. But it also highlights the fact that we biomass have got another line here. We've got a line here to commercial, residential, but we've got this line to industrial, which is the pulp and paper industry, the wood products industry. My point would be that the dominant producer of bioenergy today is not corn ethanol, with all the noise we hear about it, with all the subsidies. 9 billion gallons has about $4.5 billion in subsidies. But far more goes far more energy is produced by pulp and paper industry, recovery boilers, hog fuel boilers, and by wood products, drying, essentially, operations. I put this up because I've got a PhD in chemistry, and my PhD union card says I've got to scare any engineer in the audience with this kind of a slide. That also works pretty well with the foresters. They tend to break out in hives. But the other reason I put it up is to highlight my point with the source of the biomass matters. The reason the biomass matters is this kind of information. That biomass is made up of 3 different components. The details of those components matter on how you do a pretreatment, on how you do a fermentation, on the yield, on the productivity, the value of the biomass. So 1 ton of biomass and another ton of biomass, pine versus hardwoods, those could be maybe equivalent if you were going to gasify it, make it into these so-called Fischer-Tropsch liquids. If you're going to do a dilute acid hydrolysis, do a enzyme hydrolysis of that, dilute acid pretreatment, enzyme hydrolysis, fermentation, you know, your ton of softwoods isn't worth a hill of beans. It doesn't work. For a whole variety of good reasons, some of which we understand, some of which we don't understand. But your ton of hardwood, you know, let's talk. We can deal. Okay? So these details matter as we start to connect the feedstock, the process, and the product. There are a whole variety of activities underway. My real point is down here in Mississippi, Abengoa, and in Iowa, there are commercial scale biorefineries coming online. DuPont in Iowa, Abengoa in Kansas, and Kior in Columbus, Mississippi. Okay? So there's a bunch of researchy things going on, but there are real biorefineries coming online, as was mentioned earlier. Now, whether they're making money is an entirely different question. Okay? But they are coming online. And frankly, we should know pretty quick whether they're making money. To pick up on a couple of points, the location and the type of the biomass matters. Okay? But for these global availability things, we need to work hard, and I think a couple of the talks earlier today did a good job of going from that national or state scale down to, I want to build a plant here. Okay? And the hard part of all of that, as was mentioned, is you have to say, all right, I want to build a plant here. How much is available at what cost? And then as I think Dennis mentioned, it's who else has got plans for that biomass. But in a sense, that's what we do today across the country with almost any, you know, pulp mill, OSB mill, stud mill, what have you, right? And frankly, we do that for land with crops, with a whole variety of other raw materials. You know, is that competition for the land, for the material that comes off the land. But again, those details matter. So the three platforms, I'm going to just go through three platforms real quick. The first is biochemical. Essentially, biochemical platform does some kind of pretreatment, uses enzymes to break down the sugars, takes those sugars and makes them into ethanol, is what we commonly look at. I would personally suggest that anybody who comes up to you and says, okay, I've got this dilute acid pretreatment and I'm going to use enzymes and make ethanol, how much will you sell me your pine for? I stop reading the proposal right there. I go on to the next business opportunity right there. Softwoods and these pretreatment technologies, with one exception, and I'll come to that, simply don't work well enough to be interesting compared to hardwoods and perennial ag residues. Again, there are chemical reasons for that. We can go into that detail if anybody cares. But as we talk about ethanol coming from cellulosic biomass, that really is hardwoods and it's really perennial crops or egg residues. It is not softwood forest residue. It's not dead beetle-killed loblolly pine in the Pacific Northwest, Intermountain region. So what do these actual conversion processes look like? I mentioned pretreatment, conditioning, that's basically changing the pH. We've got enzymatic hydrolysis, fermentation. Frankly, a lot of the capital is over here in product recovery and processing of residues. Jim had a slide, I think, on the dollar per million BTU, natural gas versus wood, versus biomass. I'd pick on Jim a little bit, since he's a good colleague and a good friend, and I can get away with it, is what he didn't show on that slide, and actually I Googled it, because I didn't believe that natural gas was up to $4 a million. It is. It's up to $4 a million. It's up 50%. With all this discussion about low-cost gas, natural gas is up 50% in the last 12 months. But anyway, what that slide didn't show was the cost of the conversion technology. So you got wood, you got natural gas, both the exact same cost per million BTU. Jesse, give me a number. My number is it costs you 4 times more for the burner system for that solid biomass compared to a gas package unit. Okay? Even if they're dry, though. Now, and you had to pay something to get them dry. But, you know, so my point would be if we've got to look at that whole system. And the inconvenient reality is a bunch of these residue processing, the distillation column, are unpleasantly, uncomfortably expensive. So as we look at the system issues around the biochemical platform, you're only using the sugar. Frankly, Fermentation 101 says that only 50% of your sugar goes into your ethanol. For every molecule of your chemistry, all of you remember back to your organic chemistry, some with greater or lesser degrees of enthusiasm, but you've got 6 carbons, 6 oxygen there. For that single glucose molecule, about 52% of the mass goes up the pipe, goes up the stack as carbon dioxide. Okay? So there are a lot of conversion issues just around the mass of material. Atom conservation is the vernacular people get into. You're throwing away a bunch of what you spent time and energy growing, and you're not recovering it. Now maybe that's a good business play. The life cycle footprint could even be pretty good. But boy, can't we do better than throwing half of it away? Lignin. Lignin can be used for process heat. You got to get process heat for that distillation column from someplace. If you've got a good use for lignin, you know, you can make chemicals, you can make surfactants, you can make carbon fibers, maybe. Or you just burn it in a boiler and you use it for process heat. Okay? But there's some challenges around making that economical. To me, one of the more daunting ones is whether it's ethanol or butanol, at some point we've hit that blend wall. So you're going to make a product, and at some point you're kind of saturating a market unless you go to radically different ways of moving the material around and of using the material. Again, the analogy, maybe we can go to 15% ethanol in our gasoline, but if you really want to make take the next step, you're going to have to go to 100% ethanol in everybody's flex fuel vehicle, or E85, you know, depending on what system you like. We need to find, you know, to make this commercial, lower pre-treatment cost, and that specifically gets to the enzyme use. The pre-treatment is not per se the barrier. It's the pre-treatment has to work well enough to allow you to not use a lot of enzyme. And we can't afford to throw away these C5 sugars, these hemicellulose or xylose sugars. So one example where softwoods could be used. We do know how to make highly bleached cellulose from a kraft pulp mill. In the southeastern United States, we have about 50 of those mills. We're pretty darn good at it. All right, those things produce energy, by and large. And that cellulose coming out of that pulp mill, enzymes love it, digest it well. The problem is it's too expensive. All right, it is not an economically attractive feedstock. It is a technologically attractive feedstock, but not economically attractive. So to take a pulp mill and do exactly what we do for pulp and paper doesn't make economic sense, even though you can, you know, make a cellulose that the enzymes like just fine. Well, maybe we don't have to make that nice, pretty white piece of paper. Maybe we can do the pre-treatment with this kraft-like technology and produce a cellulose that is digestible. And so we at NC State have done a tremendous amount of work on the concept of taking a pulp mill and repurposing it. And not go into the details, but there are many attractive components. One, the assets could be used. You can probably go get $200–300 million worth of capital infrastructure really cheap at a closed down pulp mill. It's not exactly everything you want, and you're going to have to put some more money into that, but nonetheless, you can get a pretty good head start on your capital costs. Maybe most attractive in some ways is if you've got a closed down pulp mill, by definition that says there was a system in place to grow, harvest, and deliver that biomass. There is no uncertainty around it. Now again, you may not like the cost as well, but there is no risk with the production, collection, delivery of that biomass. It was there before the mill closed, it's still there. Equipment in place, it's proven. So again, low risk. I think many of us are familiar with Range Fuels, this company in Georgia that started up, had some technology problems, but also had just mechanical problems. Couldn't make their grinders, their screw feeders, a bunch of kind of simple things work reliably at the rates they needed them to work. And with a pulp mill, there is no risk to that. We got hundreds of them working around the world. We know exactly what a digester looks like. We know exactly how these systems work. You have a workforce. Again, looking at things that maybe are underappreciated, to have a skilled, engaged workforce, i.e. people that know how to make this thing run day in and day out, and know how to squeeze the last penny of operational benefit out of it, is a huge asset. And frankly, things like permitting are a big deal and can hang up many new plants. So this is borrowed from Richard Phillips, Hassan Jamil, and summarizes 6 years of work with probably 20 different industrial partners. The point I want you to take away from it is anything in green, you already had, actually green and red here, you already had in the pulp mill. All the gray stuff you got rid of, and all the blue stuff is new. So if you just kind of think about, this is an attempt to give you a visual depiction. If you bought this pulp mill, what can you use? What do you throw away? What do you need to buy new? Okay? And depending on the details of what that pulp mill had and the process details, what you want to run, that'll vary a little bit. But you can use large pieces, large segments of that capital, that installed infrastructure. Switching gears, so the second option, so that was ethanol. Ethanol 101, zoom. So now I want to switch gears and go to two technologies that try to replace that whole barrel. And where I said, all right, you're going to hit the blend wall, the 15% ethanol, and you're kind of done. So how do you get around that? So there are two ways, the so-called thermochemical platform, that allow you to make jet fuel, that allow you to make diesel fuel, that allow you to make chemicals. And they take slightly different passes at it. So let me try to differentiate them. So biomass gasification, this is what a gasification system looks like. And you're not necessarily supposed to be able to read that or understand it in detail. My point is, it's really complicated. Okay? Maybe take another shot at it looking at it this way, which may or may not help. Essentially what you're trying to do is make syngas. And once you can make syngas, right now today, there are people making anything in red, circled in red, is a commercial product. So we take syngas from natural gas, we make hydrogen, and we make reform it into ammonia fertilizer. We take syngas from natural gas, we make methanol. All the methanol in the world today is made from natural gas via syngas. South Africa takes coal, Sasol. The South African state oil company, due to apartheid, South Africa's economy ran on coal through the mid-70s. And frankly, they're still running those plants because they're really good at it, and they figured out how to make their hydrocarbons from coal. Essentially the same technology the Germans used during World War II. So you can make syngas from any carbon source. In the case of Sasol, they make syngas from coal, and they go through these Fischer-Tropsch liquids, and they make diesel fuel. They make gasoline. Their entire liquid petroleum economy runs on coal to syngas to Fischer-Tropsch liquids to all these other materials. Okay. What we're really trying to do with biomass typically is we can make ethanol directly, we can make DME, which is dimethyl ether from methanol, which is attractive in some cases, or we can make mixed alcohols. Now there are a couple of other ways that we can go at it with the biomass. So specifically, as you look at the unit operations, you've got gasification, you've got to clean up that syngas, you've got to do some reforming, some shifting, fuel synthesis, get a lot of heat and power out of this. Back again to the point that Dennis made with power integration, heat and power integration is a way to increase your thermodynamic yield. And you can, in yellow here, I've tried to highlight a whole bunch of barriers. This is taken from DOE, the Department of Energy, I just renamed that office, Bioenergy Technology Office, their barriers. So what are some of the problems with gasification? If you're making a hydrocarbon fuel, remember that my union PhD chemist guy union card slide. 40% of the molecules on that slide were oxygen. So you paid for a ton of biomass, 40% of that ton, 800 pounds, if I'm doing the math right, was oxygen. And you're throwing it away if you're making hydrocarbons. And worse yet, you don't throw away oxygen as O2. You throw away oxygen as water, where you actually have to make hydrogen to throw away the oxygen. Or you're throwing away the carbon with the oxygen, carbon dioxide. And the carbon is what you really want to sell to somebody. That's your liquid fuel. Okay? So the big downside with the thermochem technologies, by and large, they're trying to make a drop-in hydrocarbon, replace the whole barrel. And the downside is, at best, 40% of what you paid for, you're going to throw away. And there's going to be some other stuff that goes with it. The other problem with gasification in particular is these are very large plants. So the Sasol plant is basically a couple of coal mines that are directly connected to a gasifier with really, really miles and miles of conveyor belts that are directly feeding the Fischer-Tropsch, that make the Fischer-Tropsch liquid and feed it into a petroleum refinery. If you kind of do the back calculation of the caloric value coming out of that plant, it would be 30, 25, 30 times bigger than the biggest pulp mill you ever saw. Okay, that's a big plant. All right, you're not going to do that with biomass. Okay, let's make it smaller. You know, make it look like a pulp mill. Well, what did I say about capital cost? And this bigger is better. Now, the unfortunate reality for that complicated integrated system, squeezing that down to 1/25th of the size gets tough. Okay. There are other ways, DME, dimethyl ether. I bring that up because that's one way to sell the oxygen. Ether, you've got oxygen in that product. It is actually, you can run it in a diesel engine. Volvo makes a DME engine. You can, buy dimethyl ether in Sweden and run it around on a Volvo truck. Okay. It also could be a propane replacement. Okay. So it's one way to sell that intermediate oxygen. So gasification, what do we need? We need higher efficiency, and that is partly the gasification itself, but to Dennis's point, that's also how do you use all this waste heat? You've heated things up to 900 degrees C. You've got a bunch of exothermic reactions. You've had to heat up and cool down a bunch of stuff. Frankly, you're wasting a bunch of heat unless you can find a really productive use, like a small city to put next door to this thing. A small city in a really cold climate. We do need better catalysts. There are scientific, technical, engineering, chemical needs. The scale of the cleanup in particular is challenging. A bunch of these process integration things get real important. Part of this is to keep score with the life cycle attributes. Part of it is to understand if I push the scale in this direction, what happens over in that direction. There has been a lot of work in Scandinavia on gasification of spent pulping liquor. The Newburn mill in North Carolina, the Weyerhaeuser mill, ran a black liquor gasifier for a number of years. They weren't trying to make fuels there. They were simply demonstrating the gasification technology. There are a lot of materials, corrosion problems with black liquor gasification. Weyerhaeuser is no longer running that operation, but that technology is being commercialized in Sweden. What was it? Okay. So the other way to go at thermochemical that in some ways is a lot more attractive from a capital and a size point of view is the so-called pyrolysis or bio-oil technology. Essentially, you're feeding the biomass into a fluid bed reactor, you're collecting the fluid bed material, recycling that, collecting the bio-oil, and now you've got this black tarry stuff. It smells a lot like barbecue. Not all so good in a sense. looks something like this. Found a image that tries to highlight that there are a number of liquid, solid, fluid handling systems that get a little complicated. But the nice thing about pyrolysis is that is a commercial technology. People have been running pyrolysis operations at the 250 ton a day scale for at least 30 years. And when I said barbecue, I was only being a little facetious. It is a company called Red Arrow in Sheboygan, Wisconsin, and they use it for, they collect of that oil, of that biomass that goes in, they sell about 1% of the weight of that biomass coming in the door, dry weight, into the food market. They claim that if you go into your average kitchen, refrigerator, pantry, there are going to be 28 items that will have their barbecue smoke in it. Any frozen dinner kind of thing, any kind of baked crackery thing, not just the spicy pizza barbecue ones, but anything. Almost all processed meats. Okay, a lot of cheeses. This stuff goes everywhere. Soups. Okay. So my point is that not that we all should go focus on our business ventures on barbecue foods, but rather the technology for making these pyrolysis oil is something that we know how to do. The challenge then is to say, okay, now I've got this pyrolysis oil, and what I really want to do is I want to make a liquid fuel. All right, I've just saturated the barbecued smoke market with 2 plants. Now what else do I do? So what does that process look like? The problem with pyrolysis is it is not the final product. Yes, you do have this gunky oil. Yes, people have tried to burn it to replace a number 6 bunker fuel. For those of you that are, in that game, heavy diesel. You can actually burn it in a diesel engine, but it's frankly a pretty rotten fuel. It's pretty corrosive, and nobody wants to buy it. Okay. Really, it's not the final product. It's an intermediate. So you can make this at a small scale, but it is a complex mixture. It is an intermediate. The reason it's an intermediate is it tends to be reactive, corrosive, and hazardous. Other than that, it's great. So some shipping issues. What you really want to do, you're going to end up hydrogenating it. So you're going to take this bio oil that's pretty corrosive, pretty reactive, and you're going to throw hydrogen at it with some catalyst. And you're going to pull out some of those reactive components. You're going to neutralize some of those acids. You're going to take a yield penalty. But you can now make an intermediate that is miscible with gasoline. So Keor takes in whole tree logs. Go Google Keor and look at the images you can pull up. Now they've got a big log deck. They've got a big chip pile. They go into their pyrolysis reactor. They don't say it real clearly, but they go into a hydro-treating tank. They go into a barge that goes upriver to Memphis to a Valero oil refinery. Nobody says exactly, but my guess would be it goes in the side door of that Valero refinery. It doesn't go in the front door with the oil, if you will, but it goes in a side door, slightly different unit operations, but ultimately is blended in with the oil and comes out in everything that refinery makes. So the big deal there is you have just taken an operating refinery, all the distribution opportunities that it has. So that whole mixture of diesel and jet and gasoline and chemicals and asphalt and everything else they make, and if you put in 10% bio oil in the side door, 10% comes out on average in all those products. You don't need any new infrastructure, you don't need any new cars, you don't need any new pipelines, you don't need any new stuff. Just everything coming out of that Valero refinery now has got a little happy face that says 10% biomass. And if you're given credits for it, they all get credit. Okay? So it's a really attractive opportunity from the fact you can do these at the small scale. I said 250 ton a day was Red Arrow operating for 20, 30 years. Now, Keor is a little bit bigger than that, their operation. But you have the opportunity that you don't have to go to this Fisher Tropes 30 times bigger than the biggest pulp mill you've ever seen. All right, so you can start to think now about, back to James, some of your examples with distributed. You start to pick sites that may be around, 300 miles away from a central point that might look a lot like a refinery, and now all these little sites are shipping a energy-dense, higher value product. It could even go into a pipeline potentially, depending on how you upgrade at the site versus how you upgrade at the refinery. And now you can start to think about models where you do get the integration, you honor the carbon, the landscape, and you can start to balance these. So what are the challenges? We need to figure out how to make the bio-oil more stable, in particular low acid. That's going to involve catalysts, whether that's in the bed or post-pyrolysis. The supply chain gets really fun, challenging, okay? So, if you start to think of a central hub and the spoke-like ring of little tiny pyrolysis units, and now you're trying to balance carbon, money, landowner interest, and policy. Well, that's actually, you could say, well, gee whiz, that's too complicated, I give up. Or you could say, yeah, that's complicated, and that's what we do, is we start to bring analytical tools, life cycle analysis, and life cycle inventory, policy, economics, GIS tools, bring them all to bear on this challenging problem and look at these trade-offs. What we don't do in academia is figure out who actually should put money where, but that's a different discussion. And there are some demands on the refinery. Frankly, they'd just soon not actually have your bio-oil. If you hold a gun to their head, they'll take it. But there are some challenges where maybe their refinery catalyst could be made more robust. That side door that our bio-oil goes into, that has got a couple of unit operations in it that could be improved. Okay, since the two experts, Jesse and James, talked about life cycle, I'm not going to spend any time on it. But I think the question that was raised earlier that I just want to reiterate is, at some point to simply say we're biomass and we're not oil, therefore we're good, is A, analytically not very rigorous on our part, and B, frankly, not always the case if you don't do a good job with your unit operations, with your process. To say we're biofuels and we're better than corn ethanol, again, prove it. The heck with these claims. Let's get some data. Let's have a robust debate on it. I don't like your number here. I like this number over here. Let's talk about it. So life cycle is, to me, a pretty good way of doing that. Now, as James highlighted, we don't have perfect data and these systems are still underdeveloped. That's great. But it's a way to start. Requires a lot of transparency, and a lot of details get buried under pretty pictures. But as long as you've got the details and you can get them out and make that part of the discussion, I think it's a useful tool, a useful approach. What we do in particular, though, if we think about the blocks of information with biomass production, conversion, utilization, right now we have pretty good systems for knowing what to grow. Again, switchgrass and the greenwood guys growing poplar, they'd say, well, there are 30 things that we'd like to know better about our cost, our production rates, our life cycle impact. But we got examples, okay? Fuel utilization, we know how to do that. Cars go down the road. We can measure that. The real challenge, I would argue, the biggest uncertainty is the connection between what do you grow, not how much of it, but specifically what is it, and how does it perform in that conversion process? What is the conversion process? What's the yield? What are the other co-products, heat and power, or other co-products coming out of that? That's the biggest challenge. Right now, to me, that's the big hole in what we are doing. Policy, it's complex. I'll leave it to others to talk about policy, but I wanted to make it clear that a lot of this is incentivized, whether it's pellets, whether it's corn ethanol, whether it's cellulosic ethanol, whether it's an RPS for electricity. Those are policy drivers. And 2 points. What policy gives, policy can take away. I'm not as optimistic as James on whether the EU will stick to their standards or not. But the fundamental point is, whether they stick to them or not, is we're arguing that we are putting your money, our money, taxpayer money, into this enterprise for a good reason. And we need good tools and a robust discussion around why is that particular incentive a good use of our money compared to that particular incentive. I would also argue that, looking at our university footprint, that we're training a lot of bright young engineers. Some of them even came out of our department. And then I'll pick on Jesse and say, and some of them came out of our department anyway. But we have a lot of bright young engineers, scientists, technologists here, okay? We don't have anywhere near the skills devoted at that, in particular from a kind of an operational point of view that we need. Got a lot of people doing research, but getting these pilot plants up and running, getting these commercial operations up and running, is going to have significant workforce training and workforce development issues. Okay, so what I think I've hit on is there's a lot of technical risk still. We're making a lot of progress on the technology. Capital is still a huge risk. So we talk about a ethanol biorefinery as a $2, $1.50 in capital to make a gallon of ethanol, annual gallon of ethanol. For the biochem conversion, it may be $4, $1 in capital to make that annual gallon. And for these Fischer-Tropsch types of things, maybe 6, 8, 10. Big differences, dollars per annual gallon. So it's not just, is this going to be expensive, but to actually make it at scale. If you were going to say, all right, this has got a 50-50 chance of working, but it only cost me $20 million, you can go get somebody to give you $20 million for that. It's got a 50-50 chance of working, but to get it to scale, it's going to cost me $200 million. You might even get somebody to give you a loan for that. It's got a 50-50 chance of working, and it's going to cost you $1 billion. I'll get back to you on that one. All right? So that scale, it's not just, is it a 50-50 chance, but it's a 50-50 chance and a really big number. There are a lot of issues around biomass production cost. Details get real important here, and quality. The one advantage of trees, I think many of you have heard my comment before, we have this really clever storage system for woody biomass. It's called a tree. All right, so if you want fresh biomass, Dennis will go cut you a tree down. And you want some more in another month, and he'll cut you another tree down. So it doesn't have the annual harvest, and more importantly, the cost and the quality issues around the storage of that annual harvest that perennial materials do have. Wood is more consistent, harder to convert, pine in particular, biochemical, easier with thermochemical. Co-location, the value of co-location is really buying down risk. I mean, what you're saying is if I bolt this onto a pulp mill, onto an oil refinery, onto a wood-powered Craven County Wood Energy, making electricity, I've got some infrastructure there that I can start to take advantage of, and maybe I can afford to make this smaller, that A, reduces the amount of capital that somebody's got to write me that check for, and operationally gives me more time, gives me another flow of cash, revenue, out of that operation that isn't 0 or 1 based on my biofuel production scenario. All right, thank you all for your time. Daniel, thank you for inviting me.
Thank you.
Questions? Easy ones. It's after 5. I'm off the clock.
Clarify, so what my price for natural gas.
Right?
What's your price? What my current price is? Natural gas is more pricey.
Right. Yeah, I was thinking the point.
I want to, I was comparing the same. I mean, it's like I was wondering, let's try to show that wood chip price is stable. It have been stable. So if you are smaller industrial applications, if you don't have natural gas available.
Okay,
So
thank
I
you.
wanted to clear that.
Thank you. Thank you.
2 questions, I think. The first one is jet fuels. How does that fit in? We always hear folks wanting to make jet fuels, and I guess I probably explained it because it asked me. What's the best method for that?
Ooh, best and how are 2 different things. I can explain the how to do it. I wouldn't want to hazard a guess, at least not while the camera's on what's best. But no, the serious answer is on with the gasification, these Fischer-Tropsch liquids. So the example would be gasification to FT liquids. We, on our bioenergy project with Tennessee and Auburn, we've sent 75 tons of our pine biomass to Commerce City, Colorado. They made that into, we've got 250 gallons of diesel fuel. Looks just like the diesel fuel you get out of a pump. Sitting actually out at Lake Wheeler Farm. That was made out of that pilot plant in Commerce City, Colorado. If they would have turned those knobs a slightly different way, out of that plant they can make a jet fuel. They've flown a United Airlines jet on that jet fuel. And it has to do with the way you do the final cracking of the hydrocarbon. So it's biomass to syngas to hydrocarbons, and then a bunch of details around distillation and product recycle is the serious answer.
But economies of scale is the problem.
Yeah. With the bio-oil one, where it goes into the refinery side door, then whatever that refinery makes, maybe it's not making jet fuel. Okay, refineries make a whole bunch of things, not everybody makes everything. Okay, but it goes in the side door, eventually gets mixed with the petroleum that goes in the front door, and whatever that refinery is making is where, the biomass is, call it uniformly spread, not literally, but pretty close. Uniformly spread across that product distribution. So if 20% of the carbon is coming in the side door, 80% of the carbon is biomass coming in the side door, 80% of the carbon is oil coming in the front door, out the end of the pipe, out of the refinery, call it 100% of the carbon or 100% of the product, is 80-20 biomass and petroleum. Okay? So that's how the biomass would get in the jet fuel in that case. There are people, again, I'll be respectful here, there are people taking sugar to butanol, isobutanol. From isobutanol, you can go to isobutene. From isobutene, you can oligomerize that, and from those oligomers, you can make a jet fuel. And if that just sounded like a lot of steps and really complicated, it's because it is a lot of steps, and it is really complicated. Now, having said that, the example of Dow has already announced it's commercially making polyethylene plastic. So this kind of plastic, clear plastic film in Brazil, from sugarcane sugar to ethanol. Throw away 50% of the mass of the sugar. They hydrogenate it, so they get rid of the oxygen on the ethanol. Throw away another 50% of the mass. Make ethylene, and then you polymerize that into polyethylene. It's essentially the same thing with the butylene, isobutylene kinds of things. You're throwing away a huge amount of the starting material, but from a value point of view, if your ethanol is cheap enough, you can afford to do this. Or if somebody will pay you a premium for a green polyethylene. That's a commercial process that Dow's running in Brazil. Right, wrong, or indifferent from the sustainability, atom conservation, it's a commercial process. So once you kind of get down to syngas or ethylene, you can do almost anything. That's the good thing of hanging out with those petroleum chemical guys. They do know how to use ethylene and syngas.
So looking at, and that's what I always like to look at, the whole supply chain spectrum. From the point of view that, can we make ethanol? Yes, but we don't have enough residues to make it cheaper or to make it feasible. But having us that 15% cap, target, whatever we want to call it. So it looks like it makes no sense to produce ethanol from different sources if we're going to be stuck with that 15% cap into it. So looking into the technology, but into a different product. I mean, it makes no sense to make a product we're not going to be able to sell.
Well, again, so we need to be careful to differentiate. Does it make business sense for you, Chemtex, in North Carolina, to fire up your steam explosion pretreatment process, use the hog waste grown biomass, and try to make ethanol? May well, it doesn't matter if you're up against a blend wall. All you have to do is make it cheaper than a high-cost producer from corn ethanol, and you're making money. So when you say makes sense, you've got to differentiate: is it make sense for you, the commercial investor, or are you talking a national policy question and incentives? Okay, that to me would be the first question. The second one, the blend wall in some ways with ethanol is call it arbitrary. You can go to E85. I mean, there are other ways to get more ethanol into that gasoline pool, but it's not simply keep dripping it in the way you're doing it now, right? There's a fundamental step change in the system you've got to make. And I guess my point would be you have to recognize it. So as you're incentivizing certain behaviors, you say it's not just I can go from 15 to 16. At 15 you're done, unless you make another big investment to rationalize the system. And so I think moving to your underlying point, both of those facets to me then say, well, then maybe it does make more sense to go after bio oil or FT liquids. And I just said FT was pretty big. So frankly, and I think DOE is pretty well settled on this as well, that the pyrolysis oil does have a lot of attractive attributes from not needing to rearrange large systems. It's just in terms of infrastructure, fuels, how we deliver gasoline, how we deliver chemicals. But it's rather, how do you make the technology work? And if they can figure that out, you got enough, and it's pretty feedstock agnostic, not completely, but pretty feedstock agnostic. So that is a fairly attractive near term. Now, having said that, it's technically pretty tough right now. That's what we do, is worry about technology.